Not only with that.
Yeah, now
Yeah, also someone needs
now
to
he's in better club, yeah.
I think they.
No,
Maybe Liverpool's a bit better.
The Bayern is better. Yeah.
I don't know about that. I mean, Liverpool's pretty strong.
Yeah, because they have.
Their attack is really good. Their midfield is also quite decent, and the defense. I mean, they're Van Dijk good there.
Yeah.
Okay, not. I mean,
he's doing all the job.
Alexander Arnold is a striker anyway, so.
But 32 million. And Mbappe was about
Mbappe?
200, yeah?
He was 180 million. 180 million. And it was Neymar, 222 million.
Yeah, the people from Saudi Arabia, yeah.
Qatar.
Qatar, yeah.
They have unlimited access to
yeah.
money, so it doesn't matter.
They
They could also bring they could bring Messi and they could also bring all of Bayern.
They can buy anything.
But they have to stick to the financial fair play regulations.
Yeah, but that's very difficult.
Ronaldo, Neymar, everybody.
It's very difficult there because they will pay everything just to get the best.
They could also bring in protect.
Who?
They could buy you.
Oh, yeah.
Yeah.
I'm worth 400.
You can play volleyball.
Nice striker. Together with Numpy.
Yeah.
Deadly combination.
The best attack in the world.
Forget about Ronaldo. Send Messi back to Barcelona. They don't need him anymore.
Oh, Moldova, yeah.
Moldova? That's
Moldova,
Barcelona.
yeah.
I go home.
He's struggling.
Go to summer school in Spain. Wrong place.
But he's fine.
I don't know. He's good.
But he's fine.
Looks like. And he's outside and he told me if Tito wants to wait for him, he doesn't have to wait for him.
Yeah. So you can start.
Okay,
Sorry.
we can start. Okay. So yeah, we finished the confusing part about all the derivations. Did everybody write them, or is somebody still in the process of writing them? It's okay. Okay. So basically, all of this we did just for one reason, so we can actually start training the model. And here we can see we have the training loop. We have defined our learning rate. That is the constant we're going to be multiplying all the gradients, the derivations with, how much we're going to update the weights. Another thing is that you can see name epoch. It's like if you have larger data sets or something, epoch is like going through all of the data once. For example, here we have it just going through the samples that we have in stacked together. But if you have more data, you will iterate them, and once you have seen all of them, it's one epoch. So mostly training a model will be hundreds of epochs, so it will take some time. And you can see here is the model. It's a like forward function. We call this when we calculate the output. Then we calculate the loss function. And now we have two things we need. It's y prime and the loss. So now we need to implement the gradient descent for training procedure. So what does it consist of? First thing, we need to get all the derivations that we wrote all the functions. Now we just need to call them. So we can write dw1, is equal, we can write in the beginning mean, so we just get one value, because it will be, we will have derivations for each of the samples. We have 9 samples, but we care only about one value, so we'll take the mean value of them. After this, we write dw1, derivation of loss, and now we can write all the things we need. What were the inputs? W1, B1, W2, okay. So it's W1, B1, W2, B2, and after this we write Y prime, and oh, it's big Y, like this. So now we have calculated the value of this gradient. One more thing we should do, we can copy this and just change this to W2. We wrote it that we can pass all the arguments for each of the things we're calculating. And here we can change to B's. Like this, and we care about, I will look what is the output if we calculate. I'll scroll it so you can see all of them. So this is only one value. This one what we calculate is 994. We need, what shape we need? We need this over the first axis. So on the mean, we write axis equals 0. So the idea is that the shape of the derivation of weight 1 is a shape of, how can I write? Like this. The shape is 9, 9, and 4. So the two at the end are the shape of the weight that we initialized in the beginning. Here, 9 and 4. And the 9 in the beginning is how many samples we have. So we have the gradient for each of the samples. So what we want to do is take the mean over the 0th axis. So it will leave us with the shape 9, 4. It will like take the average from all the samples we had. And so I can write like this. Mean axis Viennas equals 0 is like shape 9, 4. Like this. And this we need to add for all of them. Axis equals 0. And if we run this again, we will see what is the shape. For example, for bias 1, the shape is only 9. This is what we need because we defined it as 9. But the thing here is we have a weight called 4 and 9, but the output we got from dw is 9 and 4. Thing we're gonna do is add point t. It's transpose. Everybody knows what is transposing matrix, right? Okay, if somebody doesn't know, I will show an image. For example, if you look at this, oh, I didn't switch the screens. For example, here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and you just flip it. You change columns with rows. So here we had 9 by 4, and we want to switch it to other way around. No, we had 9 by 4, we want 4 by 9. So we transpose the matrix. And now we have all the gradients ready that we want to use here.
Okay. Can you maybe explain what exactly the values of DW1 and DW2 represent? So it's the mean weight of the first layer.
So W1, W2 is the weight we're using. We have W1 is the weight. The dW is the gradient. The gradient is the value of the derivative, how much it affects the output value of the model.
But is DW1 the derivative for the edges from the input to the hidden layer? Or?
It's from the loss function till the W1 layer.
And W1 layer is
the first one. The first hidden layer we had.
input layer?
The first hidden layer we had. Hidden.
How many do we have?
2 layers. We have linear, sigmoid, and linear. So this is for the first layer. The DW2 is for the second layer.
Yeah.
So now we need to look at how we can update the weights. So all the weights we have defined as W1, W2, and etc. So what we do now is we write minus equals. Here we write dW1 times learning rate. So we just subtract from the weight this gradient multiplied by the learning rate. We subtract it because we want to minimize the loss function. If we would add it, we would get even larger loss function. The idea is to reach the 0. And we can repeat this for all of them. Minus equals, then it's dW2 times learning rate. And the same thing we're gonna add for bias. The bias 1, the bias 2, after we do this, we should see how the model trains. As you remember previously, we ran the code. We only got one value where everything was stuck together and everything was wrong. Like the price always was like 5K or something like that. And now if we run,
I'm getting an error because of the shapes.
what?
I'm getting an error message because of the shapes.
Okay, I will come look. But here you can see that the loss is decreasing. And the model is training. We can add as many epochs we want and it will go forward and the loss will decrease.
I think I found an error.
Okay. For everything else it's running?
No. I get that somewhere.
Was ist der Befehl zu sagen, okay, jetzt bist du. Ja, das ist so. Wir machen eine fortschrittliche Optimum und dann und so ein bisschen bestimmte also wir machen ja quasi immer, wir rechnen ja mit 0,01. Wir verkleinern ja immer dann ab. Wir gehen ja quasi bis zur 0. Das wird ja nicht auch mit dem 500. Das machen wir verschiedene Ableitungen. Die Ableitungen sind in die Richtung, ja, bestimmt Schilde. Und warum?
Natürlich ist das Ding gelernt, natürlich gewesen.
Das ist nur darum, warum die Ableitung ist.
Das muss man das sein.
Also ich habe halt diese Aufnahme und das erste Ding.
Ja, diesmal ist ja, Lüftung. Das hast du mir geschickt. Das ist mir doch bei dieser ersten kann ja einfach mal
the bottom one. So here is seems okay. Another one. Matrix multiplication. And another thing is also Jamboard. Here you see the expand lanes.
Probably you will say this the first level.
Expand these and then you need this. For this.
Yeah, you missed that. Yeah, and the other ones you have.
Is this near one? Okay.
What you want to expand? I think it's always when you count the first thing, you will always know who's going to pay. Transposing space, so you change the shape. So basically, here for the weight is defined as 4 9, but now to go in the
And obviously there
Yeah.
I fixed it. comes with my cross. Okay. Struggling. He made it. Trying so hard. Oh, okay. Always taking concerns. Best of culture, best of okay, I mean, it's almost like fun. Like, this song, everything, it works. So, but yeah, it's working. I would like to found a startup, and every time something goes, that's really obvious. Yeah. It's not and also, all the way. If I close it here with the customer. I don't know. I mean, Sigmoid is also in here. I don't know if you have to like make it working. No, just some, yeah. We understand yeah. Even if I mean, we all from exposed computers have similar with like Poland and Ukraine, and like we hate each other so much. But when something happens, I don't know if the Ukrainian we just know there are somewhere like dragons, yeah, it's like some doesn't say okay, it doesn't matter. Probably. Yeah, that's the. Did you like it up? It's this one. No, I did it. But oh, yeah, you didn't change. I was wondering why they have this, but this like line up, yeah, like magic.
von dem Ideal ab.
This is actually the
I still have the.
It's going around.
It's even worse.
It's not always worse, just more. Yeah, goes inside the interval of that. DB1, X0. Okay. So we go inside here. We then right there.
So as I understand, almost everyone has it working. So you look at the graph. You can see that the values are decreasing. You're getting closer to the correct prediction, but you can see the values are kind of large. For me, the loss is 3,000. So there's a problem. We always need to prepare the data. You need to know what is the data you're going to use. Because, for example, if you're talking about price of something, the value could be almost anything. Positive value, but almost anything. It can be 1 million, it can be 5. So the problem is how do we account for that? Because the model won't know. So if we go up, we can see we have a implementation of standardization. So there are two things that are available for us. One is normalization, one is standardization. So normalization is if we want to put all the data in some range. For example, you have, what's a good example? You have a raw recording of some audio with some huge amplifications, and you want to store it as a normal audio, it's -1 to 1. You can always squeeze the data in -1 to 1. That's how you store audio data. But for example, here, we don't know what is the range of the maximum input. It could be that if you want to squeeze everything together, it will scale proportionally. If there's some outlier, for example, here we have used old cars, and there's one Lamborghini, and if we scale them, the result will be close to 0, and that will be 1. So then we want to use standardization. The idea is that we take, maybe I can find a picture of that. Of what we're doing. How to best visualize it. So basically, we have a huge amount of data. It can be distributed, I don't know, however it is. But we will take the mean value and we will subtract that from all the samples. That means that the average sample will be around 0. After that, we will calculate standard deviation. This is that if we distribute it as a bell curve after some distance, so we will squeeze it. So it's not from like minus 1,000 to 1,000, but it will be approximately plus minus 5 or 10. It will be in the same range. And if we get new samples that are larger than before, they don't go over the cap. If we normalize, if we get a larger sample, it will be over 1. And the model doesn't know what to do with it. Here it will be divided with the standard deviation, and it will be in approximate range. So how can I maybe show that? For example, we have here some axes, and the samples are like something here. These are the values. First thing we're gonna do is we're gonna move it down. So the mean value is 0. So we will move it around here, like this. The next thing is with the standard deviation, we can just plot this data, get like, the bell curve, and approximately here somewhere is the standard deviation distance. And from that you will squeeze the data. This will be a divider. And for example, if here is something like, if the distribution is small, and this is like 0.5 or something, the difference will be kind of negligible. For example, one car is like value 0.5, one is 0.6, it's like hard to determine. So then we will squeeze it to this range that is the standard deviation. In this case, probably we will make it a bit bigger, or if we have it like really large, we'll squish it down. I think everybody got the idea. So now we need to implement it. And this will be kind of easy. The formula I will show now. So where's the part? Part is here. So basically, we want to change the x value. So x is, I think we need brackets. I think we need brackets. X is minus numpy mean of x, and we'll do it over axis 0. So if we have here four columns, and each of the columns represents something different, it's count of passenger seats and different stuff, and number of gears. We want to normalize, like standardize each of the columns separately, because if we see the miles, like kilometers driven, the number of liter engine will just be 0 compared to that range. So here we are calculating the x minus x mean. On the other side, we have a nice function std, and here we just add axis 0. And now the data is standardized. But what else we want to do is standardize the output. And for that we need one more thing. We want to save the values of y mean So when we transform this data, we move it and squish it, so we can transform it back. For example, if we're predicting the price of the machine, the price, for example, will be 0.5, and it doesn't mean anything for us because it's been standardized. So we need to transform it back. So now we calculate y std. Here again with y axis 0. And here just write y equals y minus y mean divided by y std. I added an image to Jamboard, if somebody is still writing. And I will go check what else we need to do now. So basically, we can now press again to train, and we will see that the loss function will be a lot smaller. You can see that this is how normally training a model, the loss looks. It firstly drops really sharply, and then it slows down a bit.
Can you repeat again the idea of that formula just to understand why we need to do that here?
Okay, so for example, the model we use, we have these weights, data can be anything in the beginning, but we know, for example, that the sigmoid is output is 0 from 1, and all of these things need to be constrained. And for example, if somewhere the value could be negative, for example, the sigmoid wouldn't work. That's why, taking account that we could have any possible data point, we have a way to, how the name suggests, standardize it. That all the possible data points are in the same form factor. That all the data points are around 0 with some fixed variance. Before it could be anything. For example, the price of the car could never be, I think, 0. It's always like few K. And now we move it around 0. The variance is not as large, and it's easier for model to calculate it, because if there's the large values, the model weights should be larger, and it takes longer time to teach that to the model. If all the values are around 0, the weights are around 0, it takes faster for the model to converge. But yeah, if you teach the model here, for example, it's really hard because all these layers are connected. Each input is connected to each of the hidden features. It's like the dot product, but the values should be for example, this is the kilometers driven is much larger than these, so the impact it has is much larger than the other ones. We wanted to take everything into account equally, so that is the goal. But here, for example, if we now go to the training loop, one more thing we could do is, before loss, we will add another print. I want which one, so we can write like this. List zip I and y print. So I don't know if you went through this. With the prints, the F before the means that it's like formatting. It will search for the curly brackets, so you can add variables inside. And here we are zipping together two arrays. As you can see how it prints. It just puts them in parallel and you make a list of them. So, but from the results, we can see that the values are not actually what we want, because it's all like negative values and stuff like that. That's not what we care about. So what we need to do before we can print and see if the predictions are actually correct is we need to go back to the values we had before. So we can write y prim disp. This will be the value we're going to display. So here is y prim. We're going to multiply it with y SDD. And we're going to add the mean value. We're going to shift it back. And we can copy this line. And we're going to do the same with the y values. because both of them were shifted away. And now if we add these ones inside the print function, you can see that the predictions are closer. That, for example, here it's like 2001, 1942, something. It's not perfect, but at least it's in the same range. Before we couldn't fit it at all. When working on like more complicated projects, there's a lot of work with the data. How you pre-process it, how you maybe make some augmentations or something else for it. It's always important to keep that all in mind, so you don't lose track. For example, here that we had the standardization, and the outputs we saw didn't make sense before we transformed it back. I had times when I spent more than a week just forgetting that I made some transformation, and I was thinking that I'm going crazy, I can't find the bug. And in the end, it was just one thing I forgot to add in the end.
What exactly is the value of y disk and y print disk?
What?
What exactly did you calculate for y disk and y print disk?
So on the top, we made standardization. We removed mean value and divided by standard deviation.
So those are the standardized values.
No, here it's back. For the model training, we use standardized, and this is for humans to see. So the values make sense to us.
It's just to speed up the model.
It's one thing is to speed up, like it will converge faster, but more importantly, it guarantees that it will converge. If the values are really large, it can just never learn. So yeah.
It cannot learn, or it will not terminate.
What?
What was the last?
No, the idea that what you want is that your model converges, that the loss goes down and everything is good, the predictions are accurate.
Okay.
But it can happen that, for example, it doesn't drop like this, but it will get stuck because some values are large, some are small. It will get those local optimum minimums, and it will just stay, for example, here. It will never get as accurate as you want it to be.
But do you know why it cannot find the global minimum?
You really never know. You just play with the parameters like learning rate, the batch sizes, the model, how many layers you have. There are some tricks, and for example, if you work on one topic for a longer time, you understand what was the problem. But it's mostly just clicking around and trying to figure out what makes a difference. So we have done this. So now the next one, I will open the next task. Here you need to get another template. So I opened 3.4. And while you're downloading it, you can upload the 3.3 results. So it's already done and you don't have to think about it afterwards. So this is the template. It's the same as I want. So now we're going to implement the same thing we had, but in object-oriented way. And one main difference is that the model will have one more extra layer, one sigmoid and one linear layer more. What that means is that if we write it object-oriented way, we don't have to worry about all this stuff. It will resolve itself. So imagine if we had for W1 and B1 4 lines of code just to calculate the derivatives. If we add one more layer, it will be 2 more or 3 more lines of code, and it's like for each layer. So we want to make an abstraction so we don't have to see that and we don't have to think about it. So now I went to the code side. So here, what happens if we run? It should download the dataset. Why it's not working? I will quickly check. If I run another one, oh no. I will just open this one, the web browser. Okay, we need to change one thing. So here, I will zoom in. Can you rewrite this one? I think you need to change something. Maybe I don't know where to copy it. The link changed that we need to download. What?
Are you sure? So for me, I need to be free at the end. So if you also throw me an arrow.
What?
So you change the dataset to dataset underscore 2, right?
Yeah.
So this also throwing an arrow. Because I looked at the server and there is like combination in dataset 3, 4, and 5.
Underline, underspace,
These are things I don't have to in this dataset here. So the only
Open it because the first thing is changed. That is changed. Okay, 1, this is 22. And the first integer is kind of large, it's changed. 1645. It's Eval's home server. He hosts all this stuff here. Yesterday it was still working. I don't know what he did in the evening. So you should be, if you run, you should be seeing the same error as I am, that something is not, cannot unpack, but at least the data has been downloaded. We don't know where to copy it. Okay, I posted it in, if somebody is still writing, I posted it in Classroom. You can just copy it from there. Yeah, that's okay. Okay, we have 1 more hour, so we need to move a bit quickly.
Could you check?
What?
Could you check? No. Sleep.
Copy this one. Just copy the link and paste here 5 minutes. Yeah, I don't know how to do it. So you have the right one. You don't have right one.
Yeah, you paste it like this.
Also das Grundprinzip ist ja jetzt alles immer auch wir müssen durchbauen, damit wir Angriff halten können.
Program it. You copy it and paste there. Where's the normal? It will download automatically. All that stuff. I'm gonna do it in December. Okay.
I will do it in dollars.
Okay.
Like 3 months in work.
Dollars?
Yeah.
No, this is
like
the new template you need. This is the new template. So it's running.
Like script.
No, because you're running.
But you need to understand it in depth.
Yeah.
You need to do it in December. Really understand.
MATLAB.
No, you do it.
Documentations for MATLAB. Like
You need to change the string. What the classroom. Last this
all the math.
copy this link. Copy the
Where do I paste the app?
yeah, this is the one.
Okay, I think everybody has it. So now we're gonna quickly do the same things we did before. This is the standardization of the data. Here we need to save all the stuff with self because we want to save the mean values and standard deviations inside. Do we need to save it? For x we don't need to save it. We can just calculate them. We can write x mean is numpy mean self x is 0, x std is numpy std self x is 0, and then we can change self x to what we want. It's like self x, we need brackets, minus x mean divided by x standard deviation. Another thing is, so we can just move this, copy the same thing for y, just change it to y. If we need it saved as in class, we will do it later when we have the need for it. For some of you, one more thing is this, where we get the x array. we can write as dot as type, and we want to write numpy float 32 because maybe some of you don't have as much RAM, and if it's float 64 it will take more memory. We just want that's another thing that a lot of neural network training is like interesting topic is what is the precision of the values you use, because it's much faster to use float 16 but it's not as accurate result, and there are the rounding errors, so basically everybody uses float 32. So if we run it on the constructor, we can see that it will go self x, how many samples we have. So in this data set we have 8,000 data points, and it's really hard to use 8,000 in one pass, so we will implement the data loader. So there we have the data. What we did? It's the same thing as we did before, the normalization, standardization of the data. So they're the same. Because the structure of the code now is a bit different, we have a class called dataset. Here we will manage all our data. Another thing we have is data loader. The data loader is the thing we had here. For example, here we just iterate the epochs, but here we will want to iterate the dataset. So the dataset is just preparation of the data. Data loader is preparing it for the model, and it will go through iteratively. So here we have train test. It should be already made for you too. And so now we're going to prepare the... Okay, so this one is okay. So now we look at the data loader. The idea of data loader is that we want to iterate the batches, the mini batches, the parts of the data we have. For example, we will use 32 samples each time because we can't use 8,000. So we will iterate them. So here we have, in constructor, we will give a data set, start index, end index, batch size. That is how many samples we use each time. And index of batch, this is how we're going to iterate. So here we can calculate, is already calculated the length, because the length of the data set is all the samples. The length of the data loader is it divided by batch size. For example, if you have 10 samples and you use 2 at a time, the data loader is only 5, because each time you use 2. So another thing is this is the inbuilt functions of the Python. Here it's iter, len. For example, if you write for a some variable like len, something like this, like an inbuilt function, you can override them. And the iter one is like if you want to do for I in data loader, it will generate this function, the definition of iter. We will override them. So only thing we do here is we write idx batch is 0, because this is only called on the first time. And when we iterate it, each loop we call the function next. And on the next we need to prepare the data. So the first thing we're gonna do is if self idx batch is larger than length self, we're gonna raise stop iteration. Like this, we will stop the iterating if we're out of bounds. So now we can write idx start and this is self IDX batch times self batch size and self IDX start. And now we want to write IDX end.
Self IDXM or IDXM?
What?
Self IDXM or
No,
just local?
just IDX end. Yeah. And here we write IDX, just IDX, this one, plus self batch size. So with the IDX start, we find where in the 8,000 samples we want to start reading, and the index IDX end is like from that place to the size of batch size. We will choose that chunk of the data. And the next thing we do is we get our x and y. It is equal of self dataset, and we just choose IDX start till IDX end, and this self IDX start we just increment by 1, and on the return we give x and y. Do you have questions about why we're doing this and what's happening there?
Yeah, can you explain that?
So maybe the confusing part is, for those who don't know Python, is the next and iter. For example, I think you did like 4 loops in some lists, but if you make this iter function for a class, it will create a generator object, and you can iterate. For example, the things you made yesterday, for each of those, if you want to iterate it somehow, for example, you had multiple objects like variables that you want to print, you can create this iter and you can iterate it in a for loop. And here we define that in the beginning we just define IDX batch that we start from 0, and here we select some chunks and give them outside. I hope it makes sense. Basically, all this stuff, when we're going to the programming in PyTorch, derivatives, all this you won't need, because this is just to understand what happens on the background, and you write the interesting part. So this is here. Now we create a data set. We can create a split. For example, we have a train test split part is 0.7. I can put a breakpoint here and see what's happening there. So,
a little bit up.
Yep.
To the line 30.
30?
Yeah, please. A little bit down. And you just say
Okay. Yep.
why did we need to define the start and the end of the batch? Or isn't it? Is it the starting point within the dataset and the ending point within the dataset?
I will scroll down. Wait a minute. When he finished, it's okay. This one.
So you have the IDX start and the IDX end variable, and is it the starting and the ending point within the dataset where you're iterating the range? You're iterating in?
Yeah.
Okay. That was the question.
So basically, the step we are gonna take is this batch size, and IDX start is from which index we're gonna start. For example, if we have a long line, we start at 0, we select 10. Next time we want to start at 10 and select another 10. So that's how we're gonna move forward. So what is this? edx start. Okay, sorry, I have a typo here. This is edx batch, the 74th line. It's not edx start, it's edx batch. Because if we're gonna multiply, we're gonna always take the same otherwise. So here we create the data set. We can see if you write len data set, the length is 8,000 samples here. Now we create a train test split. We split it, the train size is 5.6K. And the rest will be for the test data set. So here you see we define on the whole data set what is the starting index and the ending index. So we create two data sets. Another thing, what we're next doing, like here we have variable. This was what we before used in the functions to calculate the derivatives and all that stuff. Here it's only one thing called variable. We have value and the gradient. It's like the value is going forward in the model. The gradient is when we're going backward with the derivatives. So we don't have to calculate all that stuff manually. It's just here, and it will probably work.
So is the gradient the implementation of the backpropagation?
What?
Is the gradient, in this case, the implementation of the backpropagation?
Yeah. We will have it. It's like, and in the end, it's only you just call forward, loss, backwards, and it rains. You don't have to write all that stuff manually anymore. So now we want to write the linear layer. This is something we already wrote, but we will write it in object-oriented way. So here in place of we want to write variable. Inside we're gonna put that we have what we're gonna have here, the value. That's what we give, right? Yeah. Variable value numpy random uniform. This is how we initialized it previously too. We're gonna write low is -1 and size is in features and out features. And the other thing we want to define is grad. And the grad is equal of numpy zeros, and the shape equals batch size, in features, out features. Cannot variable. You can just delete this part like this. So here for the bias, it's almost the same. We add value, but the value we will have again zeros, because if we initialize bias as something large, it will screw everything up. And the shape is only out features, and we need to put them in brackets like this. And here we define gradient, and gradient is again zeros with the shape of, and the shape is batch size and out features. So basically all the gradients is the same shape as the value with added batch size. So in the end we only calculate the mean over the samples we have. Okay, the x and output we're gonna leave for now as none.
Why did you set a comma for the value within the brackets?
So it creates as a multi-dimensional array. If you just put one, it won't be correct. It will put it like.
So it signals that it has one column, like all features lines, one column.
Yeah, it's like eight rows, one column. Otherwise, if you don't add that, it's just 8. For example, it doesn't have any columns. It's like with 0, the last dimension. So now again, we have something that we already did. This is the forward pass of the linear. So the output is going to be variable. And we need to use again these squeeze and all this stuff. Self W value, because the W now is a variable, so it has value and grad. So we're gonna use only the value. It's a lot of writing now. Here is expand this from x value with axis -1. After this, we're gonna squeeze axis -1, and we're gonna add self b dot value. So this is how we calculate the output. And we're gonna save. For example, in the top, on constructor, we have x and output as none. And after the forward pass, we save them inside. We know them, so we can create these derivatives. So for the backward, the bias gradient, as we remember, was 1. And but before, we had to write all this bad stuff that we don't like. So what we're gonna do now is just you leave it as 1 plus, and you're gonna use self output grad. So now that all this data is as an object, it just can reference the gradient it had calculated for itself. And you don't have to manually use all of them. Yeah, here again with the dimensions will be. This is again Numpy expand dims of self x value. We're gonna expand axis -1. Here we're gonna do matrix multiplication. Numpy again expand dims with self output grad, and the dim now that axis we're gonna use now is -2. And for the x, I think we can just what we can steal from the previous code we had. Squeeze. Okay, I'll just write numpy squeeze axis -1. Here goes self w value multiplied by expand dims self output grad as usual, and here is axis -1, and here was G. So for example, previously we wrote everything by hand, all those things. Now if we construct model with 2, 3, 4, 5 layers, it will just call this function and it will work automatically. We don't have to think about this anymore.
What's self-output grad?
What?
What is self-output grad?
Remember what we did before, the chain rule. We started from the outermost layer, which was loss function. Then was the linear layer, sigmoid, again linear layer. So output is the output of your function.
Okay.
So you just calculate the derivative of the derivative for b is 1, and you're just gonna add all the other things added on top of this is output gradient. And I think I made a mistake, right? I needed to multiply this. The output grad is all the things we wrote before. For example, here, if we want dB linear, we know that this is 1. But the D2 is the output grad we have now. All the stuff that happened before. So we just put it inside an object. It will always know what is the right value. Okay, did you manage to write this? Okay. After this we will see if it was correct, or we need to check everything what's happening. So the next thing is we're going to define the sigmoid layer again. The self x is x, yes. Output is again variable. No, everything is going to be a variable. We're going to write 1.0 divided by brackets. So this bracket, double brackets, 1.0 divided plus numpy exponent minus x value. In Python as a programming language, if you want it to be a float variable, you just add point at the end of 1, for example, or 0.0. Otherwise, it will think that that's an integer.
Why did you set the plus in front of the NP?
Yeah.
What?
After
Why
dividing
did you set stuff?
Because I misclicked. No, I didn't misclick. There needs to be a plus. The division was wrong. Okay. So we can write the gradient itself output grad. First is value. After value we multiply with 1.0 minus again self output value, and in the end, as of the chain rule, we add self output grad. That is the one thing is for all the functions we write here. In the end, we have multiplication with output gradient. We have it here, and we have it here, here, and here. All the places. Okay. Somebody is still writing? No? Okay, we can go forward. Okay. So relo function we will leave for now. MSC we're gonna leave for now, and we're gonna implement the mean absolute error that we had before. So now we have y prime. On the forward pass, we save both of them and calculate the loss. So it's numpy mean as it was before, and numpy ABS, and we have y prime minus y. And I made a mistake that we need for both of them value because they all are variables like this, and now we have a loss and we can return it. And on the gradient side, we have self y value minus self y prime value. We're going to divide this. It doesn't allow like that. Another. It's to move it to a new line. It could be like this. The forward slash means that it's not a new line, but it's like continuation of the previous one. If it the line is too long.
Okay. Why don't you just write it in one line? Why do you need the line break?
Because the one is at the end of the screen there. It's easier to view. It's the same function we implemented in the previous template we did. So basically now we have a loss function, sigmoid function, and linear function all implemented. So we can replicate what we did previously. Okay, now we can go to the model, and here we're gonna define the layers we're gonna do. So it's layer linear. First thing I'm gonna run it in. I want to see in debug mode. What is the shape? We have 6. Okay. So input features is 6. Out features we're gonna define what we want. For example, I want 12. Then we're gonna do layer sigmoid. For that we don't define any parameters because it's just activation function. Then we're gonna do another layer linear. Here the input features is the 12 that we defined here. It needs to be the same. Out features we can again choose what we want. For example, I will choose back to 6. Add layer sigmoid, layer linear. The input features is again 6, and we're gonna predict 2 features like this. This is the model we define. And as we put them all in a list, we can use iterate them for layer in self layers. We can calculate that the output is layer, what are we gonna do? Forward from out. This is all the forward pass we have to do, because it how they're gonna execute is within each of the classes here.
So this is only forward to go to the next layer.
Yeah. So basically we have a list of layers, and we're gonna go sequentially through them. For this first, then this. So we're gonna go get all the outputs, and after this, when we want to train the model, we have to do a backward pass. And now it's much easier than it was before, because it's for layer in self layers, layer backwards. And one more thing I think I forgot is this one. Add reversed. Reversed is a function that if it's a list, it will just start from the end and go to the beginning. Because if we have a model of multiple layers, we go, for example, from left to right. And when we want to train with the backwards, we go from right to left, from the loss function to the first layer. And now the parameters function. We need the parameters function to get all the variables we had inside. For example, we have multiple layers, but within each of those layers, we have the variable W and B. So we want to get access to them. So now we iterate again for layer in self layers, and we can just check if type layer is linear layer. Here we don't need any brackets because it's a type. So each layer we defined is a class, and here we check if when we iterate the objects, if the object class is linear layer, because Sigmoid layers don't have any parameters inside them, only linear layers. And here we add variables append. We want layer W, and variables append layer B, and we want, I think that's all, yeah. And we're gonna return the variables. All these parameters we need for the next class, that is optimizer here. So it can change the values on the backward pass when we're training. This is the part where we multiply the gradient with the learning rate and add it to the weight. Okay, we have this. So now the optimizer part. The optimizer, previously what we did was only this. We got this was the backward pass, and the optimizer did only this. The gradient multiplied by learning rate subtracted from the weights. So what we want to do now is add a step function. And in the step function,
what was the step function again?
the step is the step of the optimizer. It does basically this part. It just updates the weights.
Okay, so it's the loss multiplied by the learning rate.
What?
The loss multiplied by the learning rate.
Not the loss, but the gradient, the derivative value. Yeah.
Basically, how quickly we approach the minimum.
Yeah, we are approaching it with this function. So we will call for the model a forward. We will get the output. We will calculate the loss function. From the loss function, then we can call the backwards because we have the result and we know all the derivatives with this. And when we have all the, because on the backward, what we get is we save the grad. And from the grad, we go here. We need to change the value.
Yeah.
So here we add numpy mean over param grad axis 0 multiplied by self learning rate. That's all. When we get it running, we can go step by step what is happening in each line and fully understand why it's working. Okay, so something else. So here we define, this is where we start our like model training. We define the model, we define the optimizer that we just wrote, and the loss function we're gonna use. So this is the main loop. We're gonna, for example, iterate till 1000 epochs, and in each of these epochs we iterate our train and test data set. And in each of these, we iterate the data loader. So it's a lot of loops. Yeah.
I don't know why, but I have an instance of the mean absolute error that should be created in line 252, but you don't have it in your code.
Again.
It's a variable called loss at n.
This?
Underscore n, and it should say, yeah, there it is. Should we keep it? Because it creates an error message, obviously. We need it.
The loss function, yeah, we need it. I will go through when we try to run. We will see. It should be okay. So now we are in the training loop. So as before, this part where we get the x and y is the same thing here. We got the x and the y, and we need to move, do the forward pass. So the y prime is only model forward from variable whose value is x, and the loss is equal to loss function. So loss function forward. Here I will add this. Here I will add this. Variable value y, and here is y prime, like this. So what we're doing here, we're going through all the layers. We're calculating all the losses we have. We are putting them all in a list. And after this, we have one thing we're going to do only if it's the trained data loader. And that thing is the actual training. So what we're going to do is loss function, we're going to call backwards. That was the calculation of the gradient. After this, we're going to call model backwards because we want to calculate gradient for all the layers we have. And okay, it jumps somewhere. After this, we call the optimizer step function. The step function actually updates the weights. So the model, that is the learning part. And after this, we call optimizer zero grad, that it was storing before all the gradient values of the layers. We need to delete them because they're not relevant anymore if we already did a step. And here we are adding the losses to the plot lines so we can draw. And if I'm correct, we could just run it and hopefully it won't crash. Yeah. And you can see it's working. Hopefully it's working for you too.
Und dann muss ich das ändern und den suchen. Da weiß ich genau, wo ich das weitergesprochen. So you finished with he has a failure in the code, but is it working? No, it's not. Never mind. Ja, du hast im 205. Staffel hast du einen Doppelpunkt geschrieben. Now we are finished. Really? Yes. It is worth that. Yes. Wir machen nur noch die Zeile 115 Z und D Doppelpunkt statt 2. Also, sehr genau. Wir melden uns. Now I come to me or I wrote it and I wrote this. Aber hat so viel aus der vielleicht auch noch angeschrieben. Yeah, like this. No, it should look like this. It looks like this. I will tell you if I know I have a different one. Deeper, maybe Saturday. If I quit it, I automatically operate it.
It doesn't work either. One thing about it, it's another function.
Ja, genau, dann hast du einfach versucht halt diesen Backslash zu machen. Der ist da, aber ich weiß nicht, den erkennen.
Ohne drauf.
Ach ja, stimmt, weil jedes Zeichen, was so weit drüber ist, ist halt ohne. Bei uns ist es halt wie auch. Ich drücke jedes S halt wie alt.
I will do that. I will just try to copy all this stuff in Jamboard. So if you have an error in each line, you can check it.
Schau mal aufs Handy. Schau mal auf dein Handy. Wie sie anzeigen? Hey. Wieder laden. What is this? I'm going to. Is the code good? Yeah, it's is the code copy pasteable or
What? It's not copy pastable. I don't know where to put it. If you have
you can just share it by a mail.
I can. Where to send?
Felix is going to do it, and then maybe later on, if someone needs it, I can just forward it.
Okay, you just need to give me to whom I need to send it. What? Okay, you have it working?
I guess, or I hope.
Does it run? It runs.
Yes.
And yeah, now it's stopped because it's printing outside. It will continue running because it's blocking. Yeah. Because
The problem is that this is the community version, not professional. There is what's called here, it's Python scientific that you showed me on the side.
Yeah, it overrides each step.
Can you just post it into Word and check?
It's not right? Or is it?
This one is right. This version of Python.
He said me so. Send him also.
I don't know. It's like they're using for drawing the matplotlib. Yeah. Matplotlib library, and it's like really bad. But it's the most popular. It's bad because it's ported from MATLAB, and it's using MATLAB syntax in Python, so it's like I don't know anybody who's fluently using it.
What? Python?
No, matplotlib, the one we're using for plotting, because now it
Just to see Seaborn.
yeah, so it's popular.
Ich hab's dir geschickt. Aber ich glaube, sehr geil, Programm ist nicht für uns datiert, weil ich hab halt als gedrückt Code ist, Ich hätte auch sehr schlimm auch übrigens auch das Linkswagen.
Felix, geiler Typ, deutsche Qualitätsarbeit.
Ja, das ist ein Fehler, weil ich habe einen Fehler gefunden und dann war es gelaufen. Deswegen haben wir es ja bis ins 5 Jahre so lieb und ich habe uns dann auch nicht ergänzen. Kannst du dich in den Glasraum in Google Docs oder was machen? Du musst einfach rein. Ich hätte jetzt auch erwartet, dass das geht.
Yeah, it doesn't make sense, but there's probably some type of
Okay. Four dimensions. Here.
Felix hat mir gerade meine halbe Bachelor geschlagen.
Du machst dann meine Saisonarbeit.
object from the hierarchy. So regression bachelor thesis.
The best.
It's not slow because of thinking. It's just slow. I remove the thinking. See what's like going really slow. I ran physics code and it just plotted the entire thing after like 10 inputs or something. Yeah. But you have to like move down. I mean, you don't.
Why do you think my code is going down?
You like that?
Yeah.
So also, watch the next and it will be better.
Yeah, and the best is like change or I don't know.
And in there are curves.
I don't care.
Something's happening.
Yes. And like there's like two pass things that I actually blocked out because it didn't happen.
Just use the carrot tensor. What did they win? No. Your dreams. Rugby was corrupt. Brazilian said juniors against
Mean access.
0. So they won. They tried to win. They sent under voting. And the No, really. Yeah. They were 1 line behind and then they said to the referee, I will give you 1,000 euros.
That's the big sport champion for like under 21.
What is
Serbia is sport champion for
Yeah, I've heard that they're pretty good. But
So I would, it's not
So there's something with the
It should be something with the graph. Maybe I will copy it in quickly in there. It's already in there.
Maybe I can bring it there. So
Yeah.
that would be easy.
Oh, now it's like you missed something. But I was there was like the Moldova version.
No, under 12.
Okay. Loss MSC we don't have. We have the Sigmoid one.
But Moldova is your country, so
This one looks okay. Now we're to the linear layer. Linear layers like uniform, -1, zeros, that. Numpy shapes, yes. Forward the value expanding, this one, that.
They just check for
It actually looks okay. So what is the problem? Loss, okay, loss.
I believe you. I know Serbia.
Model.
Until I met you, I didn't know that the country existed.
This needs to happen from end to beginning.
So we actually did that. I mean, okay.
But that's still the
even
problem.
if we reverse it.
Okay, that wasn't a problem then. But it was a problem. That wasn't just the main one then.
But
Okay.
once you don't have that in your code, it means that there's something.
Which
Do you
one?
have?
The
Like the
reverse?
reverse in here.
I have.
Oh, you reversed.
I have it.
Okay.
Optimizer.
see what's happened to
minus
Russia's
minus
fans.
grad
We can
grad.
find them, lots of fans. No, me, but rest of
Maybe some order something. Loss function will step 0 grad.
They are coming to
This is
us
commented
and
okay.
they were like, yeah, go to rest of
Losses.
Oh, yeah.
Why is so good behind this?
Variable.
But we want,
No,
actually,
There is no specific thing, right, that makes it like that. I mean, it should be either loss values because
There
it's like
should
increasing.
be. It should be only one thing that is the problem. We just need to find it.
Yeah.
That's the thing. Because it's probably one typo. I think somewhere the sign or something is opposite. That's the problem. But it's hard to find it.
I mean, then maybe we can look at the calculations where we are adding or
Because
subtracting. I mean, I put this minus. If it's
Yeah.
But this is the way.
yeah, but if we do it like this, what happens now? It didn't change. So somewhere else is the problem. Why prime value to do value forward.
Maybe I changed the forward function with the backward function in some place at the end.
No. Forward, backward. Yeah, it is okay. We can watch here maybe something. This seems okay.
This is the third.
ID send. This one is good. Batch. Variable. The only place where it could be wrong is the derivations. Because on the backward it learns in the opposite way.
Yes, it is doing the opposite way. That's the problem.
So if I add like this,
Everything there is at least, for example, here, I can kind of compare.
It's going better now. Like,
no, it's
no? But
it had minus sign. It's not wrong. It's still wrong.
I just reversed the whole thing.
Yeah. So it means that something is wrong with the.
Earlier. Okay. Maybe I'll just play around with the values a little bit and then it comes up like at the end.
Probably
And if
will.
we like try out something in the beginning, if it doesn't change in the end.
Probably it's something. It's as always. It's probably something really stupid.
It is. It seems so. It's very, very much. Like it makes only one defense and it's like everything's going the other way.
Yeah, I have no idea now.
Okay.
You can check maybe if they send something.
Yeah,
You can open another file and
Yes,
put a diff.
I will. That's what I will be doing.
Yeah. Maybe check it like that.
And then I get really curious now.
Yeah.
What?
It's probably one sign somewhere, so it doesn't work. So everything's working. How bad?
Pretty bad.
Again, like Fabian after 2 years.
bias. Yeah. I will check if I upload it in the Jamboard before we change it. I will quickly add it.
Yeah, it's already in
Slide number 8.
Oh,
Yeah.
they can go home.
Okay.
That was big.
Me. And here's the sample to y. Run. Something works. Something is happening. Not right.
Yeah, he's scoring so much goals. It's impossible. Too many goals. It's serious. It's serious.
No.
Serious. Look.
We are
Look how
we are
serious.
wrong. Why are we our CD?
Bigger screen.
That's what we are.
We need full screen.
Oh, much goals. Yeah.
Oh.
If you go forward, you know that what's value? What's value?
You can ask if we should watch some more videos about education. Or if we should also watch the same about message. Yeah, we're passionate about it. It's our life. We want to watch it. Oh. And Belgrade was burning. 19 minutes.
But we see that some kind of work.
Watch please. Thomas Müller.
Develop something else.
What?
Just this all it's kind of work we submitted. And it's like,
Yeah, I think so. We might manage to go having this over time already.
I was somewhere there, yeah.
Really?
Something is exploding the.
We survived the first 20 minutes and then.
And blood and protection.
How do you pronounce it?
Ja, ich heiße aber
Stella Rossa, yeah.
Just say it.
You know what? I just don't know the shop.
Yeah, Cervena. Zvezda is star, yeah. Cervena Zvezda, yeah. Red Star, Stella Rossa, however you want.
That's good.
Red Star. Yeah.
Another.
Roter Stern.
Yeah, they have chances, but.
You're sad.
Yeah.
No chance in service.
But Pablo is on fire.
But it looks like
When he scores two balls against Liverpool, he's about 100,000 euros. Take a player, yeah, and he's.
Some of my former teammates go watch it.
But he scored the goals against your million player. Yeah, money.
German hero. He's the king, he's the god. He's like Angela Merkel.
That's the best hero. Yeah,
He's still playing.
No, I think he's now.
I think he moved back to.
No, I think he's in Emirates.
son of Angela Merkel who was Müller. He's the king.
Difference there because I don't know.
That's
Right.
what's hard.
It's how it goes. It's how it goes.
This is the first one.
Where's continue? Where's study?
Yeah.
No, no, no.
Oh, because of the German power.
Yeah.
2 minutes later. Oh. Is he the electrician?
Yeah.
We could know.
In free time, he's like going to forest. He's like
Cutting
go
some wood.
It's just like dreaming. Yeah.
That's why.
I would also pick Richard.
Oh, yeah.
In the middle of the second, everybody realized that Paul is going to go. Silent.
Yeah.
Like Christian is scoring the goals.
I mean,
And right after, like, now I need to go to work.
And he's starting laughing when I was there.
let's just go to the shop here.
So before going away, one more thing. We didn't manage to go through all the stuff I had planned. There were 2 small tasks. I uploaded in the classroom a working file from what I had written today, so you can just use it. And there are 2 tasks open. They are 3, 5, 3, 6, and if you want, it would be nice if you do it as a homework. It's like kind of easy. One is squared error loss, and one is rectified linear unit. It's like 10 lines of code you need to add. For both of them, there are equations given, and you need to write them the same way we did before.
When is it due?
It's like, I don't know. It's mostly according to evals, but I think all the due dates that we're gonna check is at the end of next week. It's like, but you know, it's always better if you do it earlier so you don't forget. But yeah. So yeah, those who have something not working, you can open in PyCharm my file that I uploaded and see a diff. Maybe where is compare them. What was the difference? Because for 2 of them I couldn't find what was the problem. Everything looked fine, but for you it was training. It was untraining. The loss was going up, and for you it was just nuns all the way. Because after the first output, the gradients were like million, and it overflown. So yeah, that's it for the day. You have the file and 2 tasks to complete. Okay, have a nice day. I think we're gonna meet next Thursday. Next days will be Evals and Stefan again.